Hey everyone, so this is the video for chapter 9, lecture 1. We also going to spend 2 days on this lecture. So chapter 9 is on the periodic tables, periodic properties of the elements. So in this chapter, I'm going to be showing you, the patterns of the periodic table and to really know how to use it to the maximum extent. Okay, I always call it the big cheat sheet to your periodic table. And in this chapter, we really learn how to use it. Okay, so let's talk about the periodic table for a little bit. Its origins. So in the 1800s, it was Mendeleev that was the father of periodic table. He ordered the elements at the time by atomic mass. So in increasing atomic mass, so with the lightest element going all the way to the heaviest. And as he was doing that, he saw a repeating pattern of properties. So that's why he called this the periodic table, right? And the periodic law says that when the elements are arranged in order of increasing atomic mass, certain sets of properties recur periodically. So what he did was, instead of having, just a really long, horizontal periodic table, every time that he saw an element that had a recurring property of another one, he started a new line. So then we started having rows, okay? And so he basically put elements with similar properties, like physical and chemical properties, in the same column. And he was so good at it that he was able to predict a lot of undiscovered elements and their properties as well. So where the atomic mass did not fit, he reordered them by atomic number. So now the modern periodic table is by atomic number, not by atomic mass, right? So the two elements, for example, that he was able to predict that did not exist was gallium and germanium. Of course, at the time he called it Eka aluminum because it was underneath aluminum, and Eka silicon because it was underneath silicon. What he predicted were the atomic mass, melting point, density, formula of oxide and chloride, to pretty good precision, as you can see. The density of germanium he predicted was a little bit off, but it's still really close. And the atomic mass too, so really, really close. So it's really remarkable that he was able to do that, right? So he was really a master of observations and identifying patterns. Okay. So Mendeleev's periodic law, periodic table it's basically a law, right? And remember the difference between a law and a theory. The law tells you what is going to happen, and the theory is going to tell you the why of it, right? So for a while, centuries, we had the law, right? We had the periodic law. We were able to predict the properties of the elements, but we couldn't explain why those patterns existed. So it wasn't until quantum mechanics um, that we were able to explain why a lot of things was happening, right? And that really kickstarted a whole other scientific revolution, right? That wasn't existing before, right? So quantum mechanics really came along and just propelled us into, the modern age because we were able to figure out the why of something, right? Okay, so we're gonna go into that, right? We're gonna go into how is it that, why certain atoms, behave the way they do, why some react the way they do, based on the quantum mechanical theory. Okay. So remember Schrodinger's equation, right? The solution to that describe the behavior of electrons within the atom and where they're probably going to reside, right? And we call those orbitals, right? 3D region of space where the electrons are probably going to be. And that description there comes with a notation. So the way that we notate it is the orbital sublevel. Okay, remember the first number is the principal quantum number, and that tells you the size of the orbital and also how far away it is from the nucleus, right? So 1 is your lowest, of course. So n is equal to 1 is the lowest, and the lowest energy orbital is s, right? Because s has the L value of 0. Remember that? 0, 1, 2, 3 for L corresponds to the s sublevel. P sublevel, D sublevel, and F sublevel. Okay. So in hydrogen, right? Hydrogen has one electron, first element, right? So where does that one electron going to reside? It's going to reside in the first lowest energy orbital, which is the 1s orbital, right? So we write it as a superscript on the upper right corner for the number of electrons in that orbital. So 1s1, and that's how you would say it. Let's just say 1s1. This is called an electron configuration of hydrogen. So electron configuration, again, is just a way for us to communicate where the electron is, probably in an atom, right? We're really sort of mapping out the electron placement within the atom. Okay, so how the electrons occupy the orbitals, that is, corresponding to Schrodinger's equation, which, at this point in your education, you're not going to get what that means. But the gist of it is, and as I had mentioned before, Schrodinger's equation was solved for the hydrogen atom only because it only had one electron. Schrodinger's equation was not solved for the multi-electron atoms. It cannot be solved exactly. So these are all approximation solutions that show the orbitals to be very hydrogen-like. And so we, we keep thinking in those terms, right? But we don't have the exactly solved Schrodinger's equation for multi-electron atoms. Until we get better computers, maybe quantum computing will allow us to do that, right? But we don't have the computing power in order to solve Schrodinger's equation for multi-electron atoms. Okay, let's talk about electron spin. Okay, so electron spin is the last and fourth quantum number that you guys are going to learn. So remember, you already learned 3, right? N, the principal quantum number, which is size. L is shape. That's called the angular momentum number. And then the magnetic quantum number was ML, right? And this one is going to be MS, standing for spin, right? S stands for spin. So Stern and Gerlach were the people that were responsible for discovering the electron spin. They showed that a beam of silver atoms was split in two by a magnetic field. And so that must mean that the electrons have their own magnetic field. And it was like a north pole and a south pole that was able to be split by an external magnetic field. So then they're like, well, how does a electron have a magnetic field? Oh, well, it must have obviously it has an electric field because it's charged, but that means it must be spinning. Okay, so the spinning electric field is what generates the small magnetic field of an electron. And then that small magnetic field responds to an external magnet. And since it's split, that means that there are two magnetic fields for the electron. So that means two electrons spin. One direction gives a magnetic field pointing north, and the spin in the other direction gives the electron, gives the magnetic field of south, right? So north and the south pole. So this is what we call the spin quantum number, ms. There's only two directions for the electron spin. When it's spinning like this, okay, so that north is pointing up. You guys know the right hand rule. So if you curl take your right hand, and if you curl with your fingers in the direction of the spin, then your thumb will tell you which direction is north. So you can do that for the Earth as well, right? The Earth is spinning like this, and so North Pole is pointing up, okay? But now what happens if the sphere is spinning the other way? So then you have to go like this, and see your thumb is now pointing down. So north is now down, okay? So that's why we can just, instead of saying north and south, we call it up and down, right? Where north is up and where north is down. So spin up is this, and the opposite spin is spin down. So the MS can only have then two values, right? Because there's only spin up and spin down. Spin up will have a +1/2 as the value, and spin down will have a -1/2. Okay, so the spin quantum number is super easy, right? It is separate from NL and ML because NL and ML are related by a hierarchy, right? One depends on the other. MS is independent of that, those quantum numbers. And it only has these two values, okay? Spin up plus 1/2, spin down minus 1/2. So when you're doing orbital diagrams, remember the orbital diagrams is when you have a square and a arrow inside to represent an electron spin. A half arrow pointing up is used to represent an electron with a spin up, and a half arrows pointing down will be spin down. Okay, so it's gonna look like this. Spin up and spin down, right? Sometimes you see full arrow too, and that's fine. But I do like the use of half arrow better because the spin quantum number is plus 1/2, right? It's a plus 1/2. This is a minus 1/2. So it just kind of like gels better, right? Okay. Now when you have an orbital, the arrows, they have to pair up. So the spins are going to cancel in an orbital. So this is how it's going to work. Okay, so let's look at hydrogen first, right? Hydrogen is 1s1. Remember, that was the electron configuration. So how many boxes? So we should draw one box for the 1s orbital. Remember, there's only one type of s orbital, right? So we just draw the one box and we call it 1s. And then we put one electron in it. By convention, draw up first before you draw down. Okay, so we put the one electron, spin up in the 1s orbital, and that's the orbital diagram for hydrogen. Okay, so Pauly's exclusion principle, if you guys remember, no two electrons in an atom may have the same set of four quantum numbers. So therefore, no orbital may have more than two electrons. They must have opposite spins. So let's go over that again, right? If you have two electrons, it's like an ID for each electron. Each electron must have the same set of four quantum numbers. And so that's why you cannot have more than two electrons in an orbital, and also why they must have opposite spin. Because if they have the same spin, then they would have the same MS number, right? And that will violate Pauli exclusion principle. So within the same space, the electrons must pair. Okay. So now remember that you learned from the last chapter that the S sublevel only has one orbital, right? Because the S sublevel is L is equal to 0. And so ML can only be 0. So you only have one type of S orbital, okay? P orbitals, you have three types of P orbitals. Remember that? Because P is L is equal to 1. So when L is equal to 1, ML can be -1, 0, and +1. Right? So if P sublevel have three orbitals, now it can hold 6 electrons. Right? So each orbital can hold 2 electrons. Right? D sublevel has 5 orbitals, right? Because L is equal to 2 for D sublevel. So -2, -1, 0, +1, +2. That's 5 orbitals, and therefore a total of 10 electrons. Okay. Then we got the F sublevel. Remember, that's L is equal to 3. That's 7 orbitals, right? From -3 to +3 through 0. Therefore, F sublevel can hold a total of 14 electrons. Okay. So if you kind of just remember that, right? Remember the 1357, okay? SPDF 1357. That tells you how many orbitals there are in each sublevel. And multiply by 2, then you know the maximum number of electrons it can hold. And that, is pretty convenient to just kind of keep on top of your mind as you're doing electron configuration. Makes it easy. Okay, so now let's go to helium. Everybody, we know helium got 2 electrons, right? Of course, both of electrons are in the first energy level, and is equal to 1, right? We're still there. And by the way, here's a tip too that's nice to know. The principal quantum number, N, actually corresponds to the row number in your periodic table. So hydrogen and helium are both in the first row, right? So they both will have N is equal to 1. Okay, so now the second electron is still going to go in the 1s orbital because the 1s orbital is not full yet, right? It only has hydrogen's first electron. But when it goes in there, it has to go spin down. See that? Due to, who was it? Pauly's exclusion principle, saying that every single electron must have its own tag of unique quantum number. So if the first electron, which belongs to hydrogen, right, let's describe that first electron with the quantum numbers, n would be equal to 1, L is 0, right, because it's in an s orbital. ML has to be 0, because for L is equal to 0, that's all you can have. And then MS is going to be plus 1/2, because that's the spin up, right? For helium's second electron, right? Because helium's got 2. So helium's second electron, we can describe it again. N is equal to 1, because it's this one, right? It's this electron. It's in a 1s orbital, so N is 1. L is again 0, because again, it's in the same s orbital that hydrogen's was. ML is still 0, right? But now it's spin down, so it's minus 1/2. Okay. So now the question, right? Now you can really answer this. Why can't an orbital hold 3 electrons then? Why are we saying that an orbital can only hold two electrons? Well, if you put a third electron in here, it's either going to have to be spin up or spin down. And then what have you done? You violated Pauly's exclusion principle, because that third electron in there must share the quantum number of this first or second electron, right? There's no way around it. And so that's why we know now that there are only 2 electrons in the same orbital. Okay. Okay. So the sublevels um uh in each principal energy shell of a hydrogen all have the same energy. And so we call this degenerate. However, when you go to multi-electron atoms, the energies of the sublevels get split, meaning they're all not the same energy anymore. And it goes by the quantum number L. Okay. So if L is equal to 0, then you have the lowest energy orbital. So the lowest energy orbital or sublevel is S. And then L is equal to 1, P. And then L is equal to 2, D. L is equal to 3, F. So S sublevel is the lowest in energy, and F is the highest. That's why I've been telling you guys, right, to memorize it as SPDF, right? PDF like the file, right? And then just throw an S in front. So easy to remember, right? So that is the order of energy for those sublevels. Okay. So at this point, we're thinking a lot about what is higher energy and what is lower energy. And once we get to electron configuration, you're going to have to know that when we put electrons into orbitals, you have to go from lowest energy to highest energy. So to understand this better, I'm going to introduce to you guys Coulomb's law. And this regulates a lot of interactions between charged particles within the atom. So this Coulomb's law is E is equal to 1 over 4 pi epsilon 0, Q1 times Q2 over R. So you can see that the first, the coefficient here is just constant, right? So ignore it, don't worry about it. We are just going to hone in on Q1 times Q2 over R. I'm going to rewrite this on the board actually, because this is going to be easier to talk about on the board. Okay, but I'm only gonna just write the Q1 times Q2 over R part, not the constant. Okay, so Q1 is a charge. Okay, Q2 is also some charge. And then R is the distance between them. Okay, so let's see how Coulomb's law works. If you have Q1 and Q2 are of the same sign, so let's say that Q1 is positive and Q2 is also positive. So what that means is Q1 times Q2 is also positive, right? And R is the denominator. So as you bring the two charges closer together, meaning R is small, energy is going to blow up. potential energy is going to blow up. That makes sense because like charges repel each other, right? So when you bring in two charges that are the same, you increase the potential energy, okay? So this is going to be the same if you have a negative times a negative. Again, it's going to be positive. So what that means, again, is if you have two negative charges, you bring them close together, the energy is going to increase, okay? So like charges repel, right? So Coulomb's law is actually telling you that. And then as you increase R, the energy drops, right? Because E will get smaller, okay? So that's what Coulomb's law is telling us, right? Well, now let's switch it up. We're going to do minus, Q1's minus and Q2's plus. So when you multiply that, you're going to get a negative number, okay? So now if your R is small, meaning you bring opposite charges closer to each other, what you're doing is you're dropping the energy because this is a negative number, right? But you make the energy go large in the negative direction, which means you stabilize, right? It's a stabilizing force when you have minus and a plus closer to each other, right? Likewise, if you increase R, now you blow the denominator up, the value is going to get smaller, but it's a negative number. So a smaller negative number is actually an increase in potential energy. Okay, so what Coulomb's law is doing is just beautifully describing to us how like charges repel each other and how opposite charge are attracted to each other, right? Because it drops the potential energy if negative and positive are closer to each other. So how does this play a role in what we've been talking about? Well, in this chapter, we are concerned with where the electron is inside the atom, right? How we're going to fill it. So remember Bohr's model, your nucleus is here, right? Which is positively charged. And then you're going to have concentric circles, right? And these are basically your energy levels, right? And so on. So what we're saying is, if you're the electron outside of the nucleus, the further you are away from the nucleus, the higher the energy is by Coulomb's law, right? So as you go away from the nucleus, okay, you increase in energy, right? And this allows us, this simple rule allows us to figure out which orbitals are more stable than others, which orbital is more low in energy than others. So for example, if I ask you to compare a 2s versus a 1s orbital, which one's lower in energy? Well, the 1s orbital n is equal to 1, and here a 2s orbital n is equal to 2. So obviously, a 1s orbital is lower in energy, right? Energy increasing that way, right? Than a 2s. Okay. So that makes it easy, right? So that's how Coulomb's law works. And so, moral of the story, all you gotta know is as you go further away from the nucleus, it's an endothermic process, right? You need energy in order to get further away from the nucleus. Oh, one more thing with Coulomb's law as well, that later on is going to be useful. Since Q1 and Q2 are multiplying each other, if you have 1 minus times a 1 plus, it's a 1 negative. But if you have a 2 negative times a 2 positive, then it's a 4 negative, okay? So you can see that if the charge increases by 2 times, actually the stabilizing force is 4 times more stable, okay? So as far as particles attracting to each other, if you have high charge density particles, they attract a lot more strongly than the lower charge density particles, right? Okay, let's move on. So the effect of the nuclear charge. Okay, so really are gonna apply Coulomb's law here. So what we're gonna compare here, guys, is a hydrogen atom with a Z of 1. We know that, right? It has 1 proton. And then we're gonna compare a helium plus ion, Z of 2. That means 2 protons. And a plus means just one electron, right? So hydrogen has one electron, helium plus has one electron, and lithium 2 plus has one electron as well, right? But it has 3 protons, right? So according to Coulomb's law, which one's going to be lowest in energy? Well, here in hydrogen atom, you have a 1 plus times a 1 minus, right? Because 1 proton and 1 electron. But in helium plus, you have a 2 plus times a 1 minus. And then in lithium 2 plus, you have a 3 plus times a 1 minus. So of course, the most stable is lithium 2 plus, right? And another way you can think about it, and this is mathematically, figuring out, right? Because Q1 times Q2. Q1 times Q2 is -1 for hydrogen, -2 for helium, and -3 for lithium 2 plus. And so that's why the lowest energy is lithium 2 plus, right? But another way you can think about this is I have 3 protons that's only needing to hang onto 1 electron. That's lithium 2 plus case, okay? Versus I have a hydrogen atom that has 1 electron also, but it only has 1 proton to hang onto it, right? So there's not as much attraction, right? With just 1 proton, right? There's much more attraction with 3 protons that can hang on to that 1 electron more tightly, okay? So later on, you'll see that this will also play into size of these ions and atoms, is how strongly the protons can hang on to the electrons. Okay, the greater the attractive force, the smaller the atom is going to be, right? Because the electrons are going to be held more tightly to the nucleus. Okay. So anyways, this is what's called the effective nuclear charge. Is how many protons there are, right? Compared to the electron. So Z of 3 is going to be much more effective than, say, Z of 1. Okay, so that's Z effective. Shielding is the effect of the electron-electron repulsion. So there's always the opposing force. There's the attractive force, that's a Z effective, and then the shielding force, which is repulsive. And this is what's going to determine, the energy, right? Which one's more stable, and which one is closer to the nucleus, so the size, right? So the electron feels the attraction to the nucleus, but it feels repelled by neighboring electrons. So when we have 2 cases here, you'll see the shielding playing an effect. Let's look at the bottom picture. We have a helium plus, right? So it has 2 protons, so that's right here. And since it's a helium plus, there's only 1 electron outside. So this 2 plus is multiplying by this 1 minus, so the Z effective is 2, okay? But in this top picture, you have helium neutral. So you got 2 electrons here, okay? So the presence of the 1 electron makes the other electron easier to remove, meaning the nucleus can't hold on to 2 electrons as tightly as it can hold on to just 1. The reason being the shielding, right? The other electron's presence is pushing the other electron away, so that it makes it easier to remove. In that case, the top case, that's why you have a minus 2372 kilojoules per mole in energy, right? It's higher in energy than this one. So this one is more stable because you have a better attractive force, right? The more attraction it is, right? Coulomb's law. The more attraction it is, the more stable and low energy. Okay. And then you can also think about size here then. Remember, the size of the atom is determined by how far the electrons can extend away from the nucleus, right? That's literally the size of the atom. So in the bottom case, since the nucleus is 2 plus, it can hang on to this electron stronger. Helium plus is a lot smaller than helium, okay, for that reason. Okay, because there's no shielding, right? There's no shielding here. So the attractive force of the nucleus is a lot stronger. And so that's why we say that's Z of 2, right? Z effective of 2. Where in this top picture, the Z effective is actually less than 2, because even though it has a 2 plus pull, there's another electron kind of pushing, at the other electron. So it makes it harder for the proton to pull the electron in, right? Okay. In this picture, we have even better shielding. So here you can see again, two comparison. Let's look at the bottom. We have a lithium plus here. So we have a 3 plus charge, well, 3 plus nucleus, Z effective. And then outside, we only have 2 electrons, right? Because it's lithium plus. And they're in the same orbit, they're in the same energy level. Now, if we compare it to a lithium neutral, now we have 3 electrons. 2 of them are in the 1s orbital. One of them is in the 2s orbital, okay? And now we're comparing the outermost electron, how easy it is to be removed. The top option is much easier to remove due to the electron repulsion of the inner electrons. Okay, so inner electrons shield a lot more effectively than electrons that are side by side. Right? So this electron is much harder to remove. Right, so that's why lithium plus is lower in energy than lithium. Okay, and then we can also explain now why lithium likes to lose 1 electron. Right, because lithium plus is lower in energy, much lower in energy than a lithium neutral, right? So you can see, the black and red arrows show you all of the forces that are at play here, right? You have attractive forces, that's the black, and then the repulsive forces are the red, okay? So the red arrows demonstrate shielding, right? So inner electrons shield a lot more effectively and makes this electron easier to remove. Right? Okay, and then the third thing that we want to think about in order to figure out energy levels is penetration. Penetration has to do with this little bump in all of the s orbital radial probability distribution curve. Okay, so remember that in the 2s, there was a node, right? There's one node, and then there's a little bump that's really close to the nucleus. So that means that, you know, at this distance from the nucleus, you can find the electron. There's a significant probability to find the electron. Of course, the peak is out here, right? But you still have this little bump. So that's why a 2s orbital, when compared to a 2p orbital, is a lot lower in energy, right? And so that's why it goes SPDF, right? Because of this penetration here, right? You can actually, there's a good amount of probability that you would find the electron closer to the nucleus. Here's another picture that again shows shielding and penetration. So you have a 3 plus nucleus and 3 electrons. The picture on the left shows that this outer electron is experiencing only a 1 plus attraction to the nucleus. The reason being these 2 other electrons are shielding it, right? These 2 other electrons are pushing this outside electron further away, okay? And so it's feeling less of an attraction to the nucleus. And here's penetration, right? Penetration is this inner electron, this electron that is inside, closer to proximity to the nucleus, is experiencing a full 3 plus charge, and that's why it's so much more stable, right? Than these 2 other electrons, right? So you have a higher attraction. So outer electrons, they're not shielding, right? They're not shielding very at all, actually, right? Okay, so through the effect of, Z effective, shielding, and penetration is how we are able to order the orbitals in terms of lowest energy to highest energy for multi-electron atoms. And you can see it goes like this, right? The 1s orbital is going to be the lowest in energy because it's the closest to the nucleus, right? N is equal to 1. Then obviously, when you go to n is equal to 2, not only is that orbital bigger, but it's also further away from the nucleus, so higher in energy, right? So 2s comes next. Now, in the hydrogen atom, 2p would have been the same level, but in multi-electron atoms, it splits, right? So the 2s happens to be lower in energy than the 2p. Remember the reason? Penetration, right? The s orbital has that little bump that's closer to the nucleus. and the p orbital didn't have that, right? So after 2p, of course, it's going to come 3, right? N is equal to 3. It's even higher in energy and further away from the nucleus. So that's the 3s. And then after that, it's 3p, again, due to penetration, okay? Now, after that, you would think 3p, after 3p is 3d, since n is equal to 3, is less than n is equal to 4. So you would think 4 is bigger than 3. However, again, it's due to penetration. The 4s has the penetration, so it actually just lies lower in energy, slightly lower than the 3D. Okay, so after 3p comes 4s, and then 3d, and then 4p, and then 5s, same reason, penetration, 5s, and then 4d. Okay. So luckily, you have to know the order, but luckily you don't have to memorize it. Okay. Now I know there's some people that teach it with the arrows, but we're not going to do it that way, right? I'm going to show you guys how to use your periodic table so that you don't have to memorize that order there. Okay, so let's talk about now orbital diagram, how you're going to fill these electrons in, okay? So when you're filling the orbitals with electrons, you're going to draw, each box is one orbital. So if you were to draw the p sublevel, for example, remember the p sublevel had 3 orbitals in it, the px, py, and pz. Draw them stuck together, okay, like that, and label them p, right? And then you're going to draw the arrows inside them. You can use half arrows, okay? And here are the rules for doing it. The Aufbau principle, it's a German word, and it stands for building up. So that's your first rule, is you need to fill electrons from the lowest energy orbital up to the highest energy orbital. Just like as humans, right? When we walk upstairs, we need to walk from first step, second step, third step, right? But we, don't typically go from third step to 10 step, right? We have to first reach the first floor before we can go to the second floor and so on. So the same thing with the electron, right? Then Pauli exclusion principle says no more than 2 electrons per orbital. Just keep that in mind. And then the last rule is Hund's rule. Hund's rule is saying if you have orbitals of the same energy level, like px, py, and pz, make sure you put 1 electron in each orbital before you start pairing, okay? So this is the same rule as, I like to call it, don't be the creepy person on the bus rule. So let's say that there's an empty bus, right, and pulls up to the first station, and one person walks on. Let's say it's one of those buses where you got like the 2 rows or 2 columns, right, with an aisle in between, and then 2 seats on each side. So let's say the person goes and sits in a seat, okay? Then the bus continues to the second stop, and another person gets on. Well, this person should not go and sit next to the person that was already there, right? That would be creepy because you got all these empty seats, right, that aren't paired yet. So the most likely, right, probably, close to 100% of the time, that second person is going to go and sit somewhere else, right? And you can keep doing this until when? You can imagine the next person would do the same thing until when? When you have, uh, 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 half filled, right? And then you have to pair, right? So it's the same thing with electrons. All right, so let's do it. We're gonna start with hydrogen, right? Hydrogen is the okay, so let's start with hydrogen. Hydrogen being the first atom, right, with 1 electron. So what we're gonna do is 1s, 1, right? So the 1s orbital, you should only draw 1 box. Remember how it goes. 1s orbital, 3p orbitals, 5d orbitals, 1, 3, 5. So for s, only draw 1 box, and then there's only 1 electron in there, so you're gonna put an up arrow, okay? Now to describe that electron with quantum numbers, this is what you do. N is equal to 1, L is equal to 0, okay? because it's S, right? Remember, S is tied to 0 for L. That's the shape, right? ML is 0, so when L is equal to 0, ML can only be 0. There's only one box, right? So that is 0. And then MS is spin up, so it has to be plus 1/2. Okay. All right, let's keep going. Now we're at helium, right? Helium orbital diagram. The 1s orbital was not filled yet, so the second electron is going to go there but spin down. So let's describe this second electron with quantum numbers. N is equal to 1, right? Because it's the 1s. L is equal to 0 because it's S. ML again is still 0, right? Because L is equal to 0. ML can only be 0. And MS is minus 1/2. Minus 1/2 now because it's spin down. Okay. All right, let's keep going. Let's go to lithium. Lithium has 3 electrons now. So where's the third electron going to go, you ask? Well, to the next highest orbital. Why? Because the 1s orbital is already filled, right? The 1s sublevel is filled. It's got 2 electrons in it. So you got to go to the next highest in energy orbital. That would be the 2s. And you'll put lithium's third electron in there, okay? So to describe lithium's third electron, that's N is equal to 2. L is equal to 0 because it's in the s orbital, right? ML is equal to 0 because L is 0. And then MS is plus 1/2. Okay. Let's keep going. We go to beryllium, that's 4 electrons. So the fourth electron has to go spin down in the 2s orbital. Again, we're going to describe with quantum number. N is equal to 2 from here. L is equal to 0 because it's S. ML is 0. MS is minus 1/2, right? Because it's spin down. All right, let's go on. Let's keep going. What's after beryllium? It's gonna be boron, right? So boron, 5 electrons total. That fifth electron's gonna have to go to another orbital now, right? The 2s is full, right, guys? The 2s can hold a maximum of 2 electrons, right? So you have to go up to the next one. After 2s is 2p. But now, notice, you have to draw 3 boxes stuck to each other. Why? Because there are 3 p orbitals, right? Remember px, py, and pz. There are 3 orbitals in the p sublevel. Px, py, and pz, okay? So draw them stuck to each other, label it 2p, and then put an electron in the leftmost box. Let's go from left to right, okay? Go by convention, okay? And then up first. Now we're gonna describe with the quantum number. N is equal to 2 due to that. L is equal to 1 because of the p, right? ML is minus 1. Ooh, let's see why. Remember, when L is equal to 1, ML can be minus 1, 0, and plus 1. Oh, that's 3 values. Those 3 values correspond to the 3 boxes. So you can just label them minus 1 for the first box, 0 for the second box, and plus 1 for the third box. Does that make sense, right? Because ML, those are all the ML values for L is equal to 1. Minus 1, 0, plus 1. So just go minus 1 for the left box, 0 for the middle box, and plus 1 for the right box. Like I said, it's just from left to right. So since the electron's in the leftmost box, ML is negative 1, okay? MS is plus 1/2 because it's spin up, okay? Simple, right? Let's keep going. Next one's carbon. Now, this is where Hund's rule comes into play, right, guys? Don't be the creepy person on the bus, right? Don't make this electron go and sit with this one. There are empty boxes here. It can go into those boxes first, right, before pairing. So put that 6 electron of carbon in the middle box, and we're going to, again, describe with quantum numbers. N is equal to 2 due to that. L is still 1 because it's P. But now ML is what? It's in the middle box, so it's 0. And MS is plus 1/2 because it's pointing up. Right. Cool. Let's keep going. Now we got nitrogen. Nitrogen has 7 electrons. The 7th electron now goes in the most right box. Okay, and let's describe it. N is equal to 2. L is equal to 1. ML is plus 1 because it's in the most right box. Remember, it's minus 1, 0, plus 1. And MS again is plus 1/2 because it's pointing up. Okay, you guys see that? Okay, let's keep going. Oxygen. See how Hund's rule works? 1 electron on each before pairing, right? So give me 1 second. Lights. Okay, so this electron, right? Last electron of oxygen. See how Hund's rule works is one in each before you pair. So now you have to pair, right? So let's describe that one. N is equal to 2. L is equal to 1. ML is now again -1, right? Because it's in the leftmost box again. But now MS is -0.5. Okay. It's actually not written on the slide, but that's what it would be. Okay, so again, N is equal to 2, L will be 1, ML is -1, and MS is -1/2. Right. Okay, so you can imagine we could keep playing this game, so on and so forth, right? Okay. But let's move on. Let's do this problem. Write a set of quantum numbers for the third electron and a set for the eighth electron of the F atom. So third and eighth electron of the fluorine atom. Okay, so for fluorine, we should get the electron configuration first, so it'll be easy. It's gonna be, so fluorine has how many electrons total? 9, I believe, right? So it's gonna be 1s2, 2s2, and then remember it goes to 2p5, right? A total of 9. Okay. So we're responsible for the third and the eighth. In order to figure out the order, you have to do the orbital diagram. So how many boxes should we draw for 1s? Remember, there's only one type of s, so just draw one box. Okay, and then put 2 electrons in it. First, second. Okay, remember, we're gonna have to do third, okay, and eighth. And then we draw one box for the 2s, right? Again, there's only one type of s. First, third, fourth. So this is the third one, okay? And then we're gonna do 2p5. How many p orbitals are there? 3, right? So we should draw 3 boxes stuck to each other. Call it 2p. And then the 5th one goes in that box. The 6th one goes where, guys? Let's go here, here. Should be the middle, right? Hund's rule. Don't be the creepy person on the bus. That's the 6th. Then the 7th goes here. And the 8th goes here. So that's the one we want, right? And then the 9th one is here. Okay. So the reason why we have to do this, notice if I draw the orbital diagram and then I count over, I get the third one right, but the 8th one wrong, because I'll be like 1, 2, 3, 4, 5, 6, 7, 8. Nope. Right? So make sure you're doing it in order so you know what the third is. So for the third, let's describe it. N is equal to 2. L is equal to 0 because of S, the S orbital, right? ML is 0 and MS is, that's pointing up, plus 1/2. Okay. For the 8th electron, N is equal to 2. L is equal to P is 1, right? Remember SPDF? L is 1. And then ML, since it's in the leftmost box, I'll call it -1, right? Because L is equal to 1, ML can be -1, 0, and +1. And then MS is -1/2 because it's pointing down. Okay. Right, so that's how you do this type of problem when they're like asking for, consecutive electrons, right? You need to actually draw the orbital diagram and count along, right? Okay, let's do this one. Use the periodic table to identify an element with the electron configuration 1s2, 2s2, 2p4. So go ahead and look at your periodic table. The easiest way to, when I have a problem like this, I just count up the total number of electrons. That's 8, right? So the element is gonna be oxygen, right? And 1s2, 2s2, 2p4. Okay. And then it asks for the set of quantum numbers for the 6th electron. All right. So let's do it. Again, we need to do orbital diagram before we can answer this question, right? We have to do it in order. So how many boxes for 1s? 1. Okay, that's the first and the second electron. It's fine. Let's keep going because it wants the 6. So 2s, draw the box. Third, fourth, so that's not it. And then the 2p needs 3 boxes stuck to each other, right? Because they're px, py, pz, 3 types of p orbitals. And 4 electrons in that. So first, second, sorry, that was 5th, 6th, so that's the 6th, 7th, and 8th. Okay, so what's the quantum number for that one that I circled, right? Because that's the 6th one. 1, 2, 3, 4, 5, 6, 7, 8. All right, so n is equal to 2. L is going to be 1 because it's p, right? And then ml, it's in the middle box, so ml is 0. And ms is plus 1/2. Okay. Okay. So some terminology you guys should know. So when you have an electron configuration, the valence electrons are the ones that are outermost. So do you guys see that it's outermost because n is the highest here? So in silicon, we have 4 valence electrons, and then the electrons inside that are called the core electrons. And why do we divvy up in this way? Because valence electrons are the interesting ones. They're the ones that are involved in bonding. So later on, you're going to have to know how to count valence electrons, right? And so that's all there is to it. It's the highest principal energy shell is called the valence electrons. Right? And to figure it out, just look up at the group number. Right, pretty easy. Okay, so this table shows you, the orbital diagrams for the next period, right? We did it all the way to for a lot of the period 2. So here's the period 3. You can see Hunds were at work here, starting with phosphorus and going to sulfur, right? 1 electron in each of the 3p before pairing, right? And notice in period 3, the principal quantum number is also 3. So remember I told you guys that, right? N is the same thing as the period number, so it makes it easy to orient yourself. Okay, so what else do we notice here? Yeah, so we got Hund's rule, right? Pair, don't pair until you put 1 in each box. Alrighty. So some people are gonna teach you like this, how to memorize to for the electron configuration. I have a much better method that I'm gonna show you guys now. It is called the easy electronic configuration. Okay, so as I said before, the period number is the same thing as the principal quantum number. Okay. And then you're gonna take the periodic table and you're gonna divide it into blocks. Okay, so the S block is the first 2 columns. The P block is the last 6 columns. In between the transition metals, we call that the D block. And then the F block is down here. Okay, so why is it easier to do it this way? You don't have to memorize. You're just gonna go along and see what period you're at and what block you're at, and the orbital you're filling. So for example, the last electron of say beryllium is in which orbital? Well, look at the period number that beryllium's in. It's 2. And then what block is beryllium in? It's S. So the last electron of beryllium goes into the 2s orbital. Okay. How about the last electron of selenium? Well, selenium is lying in the P block, but in which period? Period 4. So it's 4p, right? So it makes it really easy to do configuration, and you do not have to memorize the order of those orbitals. Okay. Another thing to note, okay, how wide these blocks are is corresponding to the maximum numbers of electrons that it can hold, right? Because as you go from left to right, you're increasing by 1 electron. So if you're in the S block is only 2 wide. Why? Because there's only 1 type of S orbital, and the maximum number of electrons it can hold is 2. Okay. When you go to the P block, let's count. How wide is the P block? 6. Why? Because there are 3 types of p orbitals, and each p orbital can hold 2 electrons for a total of 6, right? Then you got the D block. D block, if you count over, it's 10 electrons. Okay. That makes sense because you have 5d orbitals, right? And each can hold 2. And then without even counting, you should know the F block is 14y, right? Because there's 7 F orbitals. Okay. Now one last rule, okay? So you're gonna orient yourself by period number and then block. Except for when you're in the transition metals, the orbital that's being filled is always n-1. So you take the period number and just drop it down by 1, and that'll be the d orbital that's being filled. Okay. All right, so have this out in front of you, okay? And we're gonna do some examples of electron configuration so you guys see how that works. All right, so let's just start with hydrogen. Easy, right? Hydrogen is 1s1. Okay. So we go to helium, right? 1s1. That's easy, right? Because hydrogen's in period 1 and it's in the s block. So 1s1. Helium, obviously, 1s2, right? And then that's filled. Now we can go to lithium. Okay. Lithium would have helium's configuration, 1s2. And then the last electron, that's the one where you look at the period number. Okay. So lithium is in period 2, and it's in the first position of the s block. So that's 2s1. So the last electron of lithium is in the 2s. Okay. Right. You guys see how we're doing this, right? Now we can keep going. Beryllium. Well, beryllium, 2s1, beryllium's in the second position of the s block, so it'll be 2s2. So it'll be 1s2, 2s2. So it keeps all of lithium's electron, right? And then you just have to figure out where that last electron goes. Okay, next up, after beryllium would be boron. Same idea, right? It's already 1s2, 2s2. It keeps whatever was there. And then now the last electron, boron lays in period 2, right, everybody? And in the first position of the p block. So it's 2p1, right? Period 2, p block, first position of p block. Got it? Right? So absolutely no memorization. Okay. Now we can even skip, right? We can even skip. We don't have to do it in order. We can say fluorine. Okay, what do we do for fluorine? Let's start at the beginning. Start at hydrogen. Hydrogen, is in period 1, right? So it's 1s, and to fill it, it's 1s2. Okay, so that gets us the helium. So put your finger on it. That's how I do it. Put your finger on helium. Now let's keep going. After helium is lithium. Okay, where are we now? We're in period 2. We're in the s block. Okay, so it's 2s. And let's fill all of that. 2s2. It's gonna get us to beryllium, right? We're not at fluorine yet, so we just keep going, right? And then after that is boron. Boron is in period 2 and is in the p block. Okay. And then we can go all the way to fluorine, right? Fluorine is, keep going, is in the 1, 2, 3, 4, 5th position. Okay, so boom, done. See, no memorization. Right. Let's go to sulfur. Let's try sulfur. All right, from the beginning, right? 1s2 gets you to helium. 2s2 gets you to beryllium. And then what's next? Now we're at the p block, so it's 2p. We're gonna fill it all the way because we're not anywhere close to sulfur. So we're gonna all the way to neon. All the way to neon would be 2p6, right? And then after neon is sodium, so that's in the 3s, but we're gonna fill all that too because we're still not at sulfur. So it's 3s2. Okay. Then after that, so 3s2 gets us to magnesium. Then the next block is p block, aluminum. Okay, so 3p, but okay, S is in 3p. Sulfur is in 3p, so 3p. Sulfur is in the 1, 2, 3, 4, fourth position. 3p4. Okay, you guys see that? Okay. Let's try one with a transition metal. So let's do titanium. We're gonna do the from the beginning, right? This is called, by the way, this is called the long version. I'm gonna show you the short version, the condensed electron configuration. Or not long, but full, which is long, right? So it's a full electron configuration. So full, you start from the beginning, start hydrogen 1s2, 2s2, gonna do a little quicker, right? We know this now. 2s2 gets you to beryllium, then 2p6 gets you to neon. I'm still using my finger. Then 3s2 gets me to magnesium, and then 3p6 gets me to argon. And then after argon is potassium. That's 4 in the 4s. 4s2 gets me to calcium, and then titanium is in the D block. Remember, when you get to the D block, you're gonna drop the period number down by 1. Since titanium's in period 4, I'm gonna drop it down to 3, and I'm in block D, so it's a 3D orbital, and titanium's in the second position of the D block, so 3D2. Right? Just like that. Okay. All right. Let's do one more. Let's do nickel. Okay, nickel 1s2, 2s2, 2p6. Right, we keep going. 3s2, 3p6, 4s2 gets us to calcium, and now nickel is in position 1, 2, 3, 4, 5, 6, 7, 8. So 3d8. We're at the D block. Remember, drop it down by 1. So nickel's in period 4. Subtract 1 is 3. So it's a 3d and then 8. Okay. All right. So now let me show you guys the short configuration. So you see sulfur. I mean, can you imagine if I assign like a bigger atom? It's going to be really tedious. So for, most purposes, if I don't specify, it's okay for you guys to do short electron configuration. But if I say do full electron configuration, then do start at hydrogen 1s2, 2s2, and so on, right? So here we go. We're gonna do the short. This is how you do it. If I say do the short configuration for sulfur, you're gonna move left. Always move left. Move left to the previous noble gas. That would be neon. Neon's configuration is 1s2, 2s2, 2p6, right? This is neon's configuration. So literally, you'll just go brackets neon. 3s2, 3p4. Okay, so backtrack, put your finger on neon, and then go forward till you're at sulfur. So at neon, you go forward, it's 3s2. You keep going, it's 3p4. So in the short configuration, what you're saying is sulfur has the same electron configuration as neon, and then some. And what is the and then some? 3s2, 3p4. Okay. Let's do it for this one, titanium. Look at titanium, walk back to the previous noble gas. Oh, it's argon, so put that in brackets. And now go forward until you see titanium. So it'll be 4s2, 3d2. Okay, so you don't even need to get titanium long configuration, right? You can just do it short right away. Okay, so with nickel, let's just do it short right away, right? Nickel, walk back. Again, it's brackets argon, and then keep going. 4s2, 3d8. Okay. Alrighty. Let's do niobium for fun. Or no, let's do yttrium. Let's do yttrium. We're gonna do short. So yttrium is Y. Go back and you see the previous noble gas is krypton. Krypton, then you walk forward. We're at 5s2. Okay, and then yttrium's in the D block. Remember, drop it down by 1, so we're in period 5. Drop it down by 4, so that's a 4d. And yttrium's in the first position, so 41. Okay. All right. All right, now let's do chromium. Let's do chromium. Put your finger on chromium. Walk back. Oh, previous noble gas is argon. Put that in brackets. Now walk forward. You're probably gonna put 4s2, right? 4s2, and then chromium's in the fourth position. Period 4, drop it down, so 3d4. That's probably what you're gonna put. Now let me show you. There's an exception here, okay, to this easy electron configuration. Of course, there's always exception to any of these rules, this is one of the first ones. So let me show you why this is not it. It's actually 4s1, 3d5. Okay, that's the actual configuration of chromium. So it's not following all rules here. And what is happening is one of the s electron is going into the 3D orbital, right? One of the s electron gets added to here, so it becomes 4s1, 3d5. You still have 6 valence electrons, right? But they're just it just got moved. So let's see why that is. Let's draw the orbital diagram for 4s2, 3d4. And we'll see why it prefers this configuration. So for 4s2, for 4s orbital, we're just going to draw one box, okay? And then 3D, I'm going to draw it a little higher because the 3D is a little higher in energy than the 4s. And how many boxes, guys, should I draw for the 3D sublevel? How many d orbitals are there? 5. 3, 4, 5. So 1, 2, 3, 4, right? 3d4. Okay. All right, so let's draw it for 4s1, 3d5. Okay, so it prefers this configuration, which means this configuration is lower in energy. Okay, let's try and explain why that is. So what's happening is this electron is being promoted, and it has to go up in energy in order to occupy this box. Okay, so that's a cost, right? It costs energy to put this electron up there, but it also costs energy to leave the electron there. Why? Because of electron-electron repulsion. If you put this electron here, it alleviates electron-electron repulsion, right? Whereas if you left it there, it would be repelled. However, if you put it up there, you have this cost of moving it upstairs, right? So there are two costs here. This cost is called promotion, okay? So let's say that that's the energy of promotion, and then versus the electron-electron pairing energy. Okay, well, let's call it repulsion. That's easier to understand. Okay, so in this case, since it prefers this configuration, it means that the electron repulsion, the energy of repulsion is greater than the energy it takes to promote it. Okay, does that make sense? So it's more detrimental for the repulsion than it is for the promotion of the electron upstairs. Okay, and so that is what we tend to see. This electron-electron repulsion is always worse. So when you can spread out electrons, do it. So what you end up is having a half-filled 4s subshell and a half-filled 3D subshell. Okay, so this is going to become our rule now. Okay, that's the exception, is that whenever you can have half-filled or fully filled sublevel are preferred. Okay, so here you have this one fully filled, but this, this is not half filled. Here, this configuration better is because it's half filled. The S sublevel is half filled, and the D sublevel is half filled, right? It has 5 out of 10, right, or 1 electron in each box. So basically, it wants 1 electron in each box, or it wants fully filled, which is everything paired, because that's just more energetically stable, right? So let's look at copper too. Okay, let's do the electron configuration for copper. So if you look back at the previous noble gas, it's argon, right? And you keep going, you'd be like, oh, 4s2, 3d7, or 3d9, right? Yeah, 3d9. But wait a minute. If you do that, one, two, three, four, five, six, seven, eight, nine. Okay. Huh. No. What if we take this electron and put it up here instead? We could have this one half filled and this one fully filled. So that same thing happens with chromium is one electron from the S goes up into the D. So 4s1 3d10 is copper's electron configuration, right? So guys, how can we just remember this exception? Go by the group number. What was chromium's group? 6. And what's copper's group? Group 11. So group 6 and group 11 have these exceptions. Or let's say have this configuration. And it's the exception to the rule. Say that, right? Okay. So group 6 and group 11 have this configuration, meaning the one electron goes from S to D. Okay. So remember that every time, right? So what other elements would have that kind of configuration? Molybdenum, right? Silver, gold, right? On group 11. Okay, last slide here. Okay, so this is just summarize what I said, right? Expected versus found experimentally. There's even more exceptions. So look at chromium, right? That was the one that we just talked about. We expected 4s2 3d4, but it's actually 4s1 3d5. Copper 4s2 3d9, but it's actually 4s1 3d10. Niobium 5s2 43, 5s1 44. Again, alleviating electron-electron repulsion. It kind of likes that, right? Molybdenum 5s2 44, it becomes 5s1 45, right? Again, that's molybdenum is in chromium's group, so not a surprise, right? Then ruthenium, again, spreading out here, right? 5s1 47. Palladium is a really interesting case. Palladium should be 5s2 or expected to be 5s2 48, but then it took both of its electrons from the s orbital and put it in the D, so that you have a fully filled shell and then empty, right? Empty and fully filled. So there's something about the energetically favorable things of electrons pairing, right? That we see over and over again, right? Okay, so that's it for this chapter, guys. I'll see you again next time to finish chapter 9.